Okay, so what we have achieved so far, so like we are calculating directional derivative. So if we have x-axis and if we have uh, x-axis and y-axis and there is a surface, this is xy plane, then we can calculate the kind of its derivative of a function. So we have a surface xy, we have two independent variables x and y, and x is a kind of independent in the sense that it would vary along the x-axis and y would vary along the y-axis. So they will vary on the surface xy plane. So the function over xy is fxy. Okay, so z equal to fxy, and then now I want to calculate dz by dx. How much z would vary per unit change along the x-axis? How much z would vary per unit change along y-axis? So dz by dx, dz by dy. So dz by dx is also called fxxy, fx braces xy, and dz by dy is called fy braces xy. So fx xy, fy xy are the partial derivative along the x-axis and along the y-axis. So if I have a function fxy, then partial derivative how much z. So if this is a surface, okay, so if this is a surface, then x and y would vary in this plane, whereas z would vary vertically. Okay, so if I have equation called 1 minus x square minus y square, this is constitute a sphere. Okay, so if this is a surface on which x y would vary, then the height x y would vary as an independent variable, then where the dependent variable, that is z, would vary vertically. So 1 minus x square minus y square, so this will lead to a sphere. Okay, so this is the concept. Now, how much z would vary per unit change in the x, that is dz by dy, dz by dx, keeping any y as constant. So that is called partial derivative of fxy along x-axis, partial derivative of fxy along y-axis dz by dy. Now, question comes is, what if partial derivative of z along x-axis is dz by dy, partial uh, partial derivative of z along y-axis is dz by dy, then what is derivative of z along any vector u in the xy plane? Okay, so dz by du, dz by du as per the differentiation it is, so now we'll calculate dz by du at any point a comma b. Okay, so dz by du, if we want z differentiation, dz by du means along u vector, if there is a change delta u, then how much z would change. So this is a point that is called gamma. Gamma is a point. At gamma point there is a z like this. Then gamma plus delta u, there is another z. Obviously there will. So if I differentiate these two z and then divide by delta u, what is the value? dz by du. Variation of z per unit change in the direction of u vector. Okay, so this is what is required to be calculated. Now, as per the differentiation, if we want at point a comma b, then fa plus delta ux, delta u is the length on which we want the change. So z at at variable gamma, that is a comma b. So z, the vertical height at a comma b, and vertical height at a comma b plus delta u. So it cannot be said a comma b plus delta u. So a plus delta ux comma b plus delta uy. So if there is a delta u is the we want to calculate its component in x-axis and its component in y-axis. Please refer our dot product and cross product video. What is component and how is energy? We say that how energy someone feels when he stands on x-axis, because vector are nothing but energy sources which has a direction and strength, nothing more than that. So if we go for the if we go for the differentiation, if we go for the differentiation, then differentiation of z at point a comma b, that is a point on any vector u, is f a plus delta ux comma b plus delta uy, where delta u is the displacement on which we are calculating the differentiation. Like if I want to calculate dz by dx, then at any point x will change a delta x variation, and then z at x plus delta x minus z at x divided by delta x. So that is per unit change in x, how much per unit change it brings in z. So in u direction, the value at gamma plus delta, that is a z, and value at gamma, that is a z, if we differentiate, if we subtract and then divide by delta u, that is the displacement. If that is the displacement, how much the displacement in x coordinate is it's we can say energy essence in x coordinate, or mapping in x coordinate and mapping in y coordinate. So ux uy. So f a plus delta ux comma b plus delta uy minus f a b divided by delta u. Okay, so this is dz by du. Now one way we can calculate is, we can calculate like that. Like if I have now, if there is a u vector, then there would be equation for u, like 2i plus j. 2i plus j is the equation of a line. So I can say if z equal to 1 minus x square minus y square at any point 1 comma 2, what is its directional derivative along a line u, that is 2i plus j? This would be the question. If z equal to 1 minus x square minus y square at any point 1 dot 2, what is its directional derivative in the direction vector 2i plus j? Okay. Now, to calculate that, we are calculating f a plus delta ux comma b plus delta uy. That is the z value at delta u distance from a point a dot b minus f a b, z at a b divided by delta u. Now if I have the equation of line, then I can convert it to unit vector. Okay, so if I convert it to unit vector, I will just divide by its strength, that is the hypotenuse of the length square plus width square. So now we will reconvert our, if it is 2i plus j, or if it is I plus j is the u vector, then unit vector will be 1 by root 2i plus 1 by root 2j. Okay. Now we are taking any distance delta u. Along the delta u, what is at both side z is, we subtract and divide by delta u. If that is the case, then what is delta ux? So delta ux is nothing but whatever the unit vector we have taken, its x component multiplied by delta u. What is delta uy? Its y component multiplied by delta u. Okay. So fa plus delta ux b plus delta uy minus fab divided by delta u. So fa plus delta u would come as a plus 1 by square root 2. My u equation is I plus j. Unit vector will be 1 by root 2 I plus 1 by root 2 j. So unit vector's component along the x-axis is 1 by root 2. So ux is 1 by root 2 multiplied by delta u. Uy is 1 by root 2 multiplied by delta u. I plus j is u vector along which we want z dz by du. If I plus j is a u vector, then unit vector is the vector divided by its strength. So that will come 1 square plus 1 square root 2, a square root. Then unit vector of u is 1 by root 2 I plus 1 by root 2 j. If that is the case, then for any distance delta u, its x component would be 1 by root 2 into delta u, 1 by root 2 into into delta u, uy will be also like that one. If that is the case, now we can calculate dz by du, placing so f a plus delta u. So any point we can take like 1 and 2. So 1 f a is 1 plus 1 by root 2 u, root 2 delta u, okay, and b is 2 1 2, then 2 plus 1 by root 2 delta u, whatever we have taken, minus then f 1 and 2. So f a plus delta ux comma b plus delta uy minus f a b divided by delta u. So whatever it comes, now we can calculate. So f whatever it comes, that is dz by du. So the derivative of 3D function fx y or z in the direction of vector u at point 1 dot 2 or at point a comma b. So, but what is the problem with this solution? The problem with this solution is that it is not generic. We have to find A and B, and then we have to manually calculate ux and uy. And for every scalar A and B, we have to manually find. So there is no equation. But anyway, since the basics of differentiation falls under this formula only, that if we want dz by du, then fa plus delta ux b plus delta uy minus fab by delta u. If we want dz by dx, then fx plus delta x comma y f minus fxy by delta x. So that is partial derivation. So this is a general concept. So based upon this principle, we can calculate dz by du, directional derivative along the u. But this is not generic. If this is not generic, then with the equation, with the 3D equation, that is 1 minus x square minus y square, that is fxy. That is the 3D equation and the equation of the u vector. Now we have two data. U vector equation, that is I plus j, we can say, and equation in the 3D fxy, that is 1 minus x square minus y. With these two, we cannot calculate the generic directional derivative. Directional derivative of xy along the vector u, we calculate. Either we can go with the differential equation, that is fa plus delta ux b plus delta uy minus fab by delta u, and then we can find the unit vector and then we substitute and we find the value. Or if you want generic, but then how we can calculate? So idea is we need a delta z change. What is change in z? If there is change in delta u, for delta u change in u vector, how much is d delta z? Delta z by du we want. Per delta u change, how much is delta z? Delta z is through 1 we found out fa plus delta ux b plus delta u minus fab by delta u. But fa plus delta u b plus delta uy, fa plus delta ux b plus delta uy, this we cannot find through the generic equation. So we want one more equation. Okay. So the concept is that we want one more equation. With these two equations, it's not possible to find generic. We can now take any a and b, and then we can take any delta u, and then you can find what it is. But it is not generic. If it is generic, then because we cannot find delta z based upon fa plus delta ux b plus delta uy and minus fab. So if I subtract this, I get delta z by delta u. So delta z we cannot get like this. So what is the solution? Okay, so solution is there is a concept called so we solution is we have to find another equation through which we can find the z. One equation of z is z equal to fxy. That is z equal to 1 minus x square minus y square. This is what we have taken. What can be the other way we can calculate the z? Like this is the sphere, okay, and if I keep focusing on the sphere, okay, zooming in at some point, can we see? So there is something written here, okay, so there is something written. So like someone can see this is a sphere. If I bring in near the camera, can we see a sphere is becoming flatter. Now it is almost flat. We are standing on flat earth. See, down the line, it is complete flat. But if I see this from moon, it is sphere. So if it is a sphere, and if we keep zooming in, and then at we reach at a place on the sphere surface where it is on the sphere, it is a flat line. This is called local linearity. If I have a curved line like this, if I keep start focusing it, we will reach to a point where it will look like a straight line. So that is a tangent. Okay. So we are saying my earth is flat. Okay. Anyone would say that earth is flat because we are standing on the tangent. If someone starts from the moon and keeps zooming in, and he comes here, he will say, I started from a sphere looking, but no, it looks flat. Because you are standing on the tangent. That's why it looks flat. Okay. If that is the scenario that it looks flat, then it is called local linearity because local point is linear. Okay. If that is the case, then you are standing on a tangent. If that is the case, then what is the equation of the tangent? Equation of a tangent, if it is a line, then it is y equal to mx if it passes through origin, where m is dy by dx at that location. If I try to find equation of a surface, because if I take the tangent on the 3D, it will be a surface. If it is a single line, then it is tangent is also a line. If it is a 3D object, then tangent would be a surface. Okay. So the surface, if I try to take tangent, that is the partial derivative. So I can take tangent along x-axis. I can take tangent along y. I mean, I can take partial derivative along x-axis, and I can take partial derivative along y-axis. So that is dz by dx and dz by dy. If that is true, then approximately, I won't say that is for sure, but approximately the at any point, because tangent would vary, equation of the tangent would vary point to point. At any point x comma y, the equation of the tangent would be m1x plus m2y, where m1 is dz by dx partial derivative along x-axis and m2 is dz by dy partial derivative along y-axis. This is approximation. Okay, so now if I say that please give me complete equation, so it will become as z minus z0 the way, because please go through the zero vector tutorial, zero vector video. So everywhere zero is hidden. If I say z equal to m1x plus m2y, zero is hidden. So z minus 0 equal to mx minus 0 plus m1x minus 0 plus m2y minus 0. So that is z minus z0 equal to m1x minus x0 plus m2y minus y0. So z0, x0 and y0 are their intercepts on their axes, or when the surface passes through x0, y0 and z0 point. If that is the case, then equation is z minus z0 equal to m1x minus x0 m2 y minus y0. Okay, so this is called local linearity, means we are calculating tangent at any point x and y. If that is the case, then this is the equation of the tangent. Okay, so pretty nice. if I have the equation of the tangent, so this is equation of a line irrespective of whatever is the equation of in the 3D. So if this is the equation of the surface, then at any point xy, then if I substitute xy to the actual point, then I can get the z. We got another equation for the z. Z equal to m1x plus m2y. Considering it is passing through origin, we got equation of z through tangent. So nice, right? So now if I have dz by dx, that is m1, that is partial derivative, or fx xy, fy xy, that is dz by dy, then dz by dx. Now if I say I want to calculate local linearity surface or tangent surface at point A dot B, that is the point of contention, right, till now. So at the point A comma B, what is the tangent, that is dy by dx, dz by dx at A comma B, whatever it comes into x, plus dz by dy at point A dot B, A comma B multiplied by B, A dot B we want. So if it is a sphere 1 dot 1 minus x square minus y square, then dz by dx is minus 2x, dz by dy is minus 2y. So in that scenario, dz by m1 into x, so at point A it will be minus 2ax minus 2 minus 2ax and minus 2by. Okay, so z equal to minus 2ax minus 2ay at point AB. If I substitute x and y with a and b, we get minus 2 square and minus a minus 2a square minus 2b square. So this is equation that it passes through origin. Originally we had minus 1 minus x square minus y square. Okay, so why it is not sum? Because we have not taken care of intercepts on the axis. If we take care, then it will come exactly like that. So we have another equation, that is z minus z0 equal to m1 x minus x0 plus m2 y minus y0. Consider this full equation. Now, what is now our concern is, if we want dz by du, then I have to calculate delta z by delta u. Per delta u change in the u direction, I have to calculate delta z. Per delta u change, I want delta z. What is delta z? If z equal to, if if delta z, so if z equal to z minus 0 equal to m1 x minus x1 plus m2 y minus y0 x minus x0 plus m2 z minus z0 equal to m1 x minus x0 m2 y minus y0. Now if we want delta z, okay, so if we have delta u, against delta u there are 2 points, 1 point, 2 point. At this point what is z? At this point what is z? Subtract it, divide by delta u. This is what we want to calculate the directional derivative of z along u, the dz by du. If that is the case, the delta z, now one point is m1 x1, m1 x plus m2 y. Another point is one point is m1 x1 plus m2 y1. Another point is m1 x2 and m2 y2. So there are two z. One z is m1 x1 plus m2 y1. Another is m2 x2 plus y2 m2 y2. So one is a and b in the x and y term, and another area is a plus delta ux and b plus delta uy. So we have 2 points. One is a, b, and another point is a plus delta ux and b plus delta uy. At both locations we have to calculate z and differentiate. If that is the case, then we have z equal to m1 x plus m2 y. Now if I take at these 2 points and then do the delta z, the delta z would be m1 delta x plus m2 delta y. I mean m1 delta ux plus m2 delta uy. Can we get something? Now delta z we calculated. So delta z, if z equal to m1x plus m2y, two location of z we will take. One is m1a plus m2b, and other is m1a plus delta ux and m2 m2 uh, b plus delta uy. If we subtract this, we get delta z. If we get delta z, that is m1 delta ux plus m2 delta uy, we are getting something. Okay, so probably we can discuss that, but we'll discuss more on the local linearity. So local linearity is a kind of stuff that gives us the tangent. So how we can say that z equal to m1x plus m2y. Now, suppose that this is x-axis and this is y-axis. So this is the surface, and this is the tangent along x-axis, and this is the tangent along y-axis. So rather, I would say this is the tangent along x-axis, and this is the tangent along y-axis. What I'm trying to say is that if this is the surface, then if this is the xy surface, then z is varying like this along x-axis. So with growing x, z is decreasing, but with growing y, z is increasing. If that is the case, then if there is a variation in x, then z is decreasing, while there is a variation in y, then z is increasing. If that is the case, then we have to add both. Like we saw delta z equal to m1 delta ux plus m2 delta uy. So dy by dz by dx, that is m1. So if I start from here and suppose that the variation along x is -1 and variation along y is 2, then for 1 unit of change along x, change in x-axis brings z one down, whereas 1 unit of change along y-axis brings one up. So dz between these 2 points, one point we started and one point we went. So we started from a point, then we came down in x-axis, then went up in y-axis. This is one point, last point. First point, down in x-axis, up in y-axis, another point. If there are 2 points, what is delta z? Delta z is how much we come down and how we come up, we add it. So both slope we have to take care, and then we multiply each slope by what is the amount that we are traversing. So delta z equal to m1 delta x plus m2 delta y, or delta z in our vector term, delta z equal to m1 delta ux, the delta u's component along x-axis, plus m2 dz by dy, okay, and then delta uy. So now delta z by delta u with another equation of z, that is tangential equation of local linearity. We have del m1, that is dz by dx, delta ux plus m2, that is dz by dy, delta uy divided by delta u. This is, we got another equation for the directive differentiation. Okay, so directional derivative of a function fxy along vector u. Okay, so now we'll proceed slowly that what it is, how it is so nice and so important and so generic.